Welcome back. This is Rashish. So we already did the first part of the delay. In the second part, we will look into further details. So this is our NMOS circuit. From the whole inverter, I have taken the NMOS. Let's understand that. And the PMOS will be similar. So in this one, we have input voltage, output voltage is here, right? When you, in order to understand how output voltage is impacted by resistance and capacitance and how then input becomes output, let's understand a model. Okay, I won't take you through too much details of modeling or mathematics, and I really want to make you understand the resistance and capacitance part, but bear with me. So in this transistor, typically transistor you cannot because on the input side there is no current flowing. There's really capacitor here that you are charging, and as a result of that capacitor, this current is driven or impacted. So typically transistor is always kind of connected on the input side equivalent model and output side equivalent model. On the input side is literally a voltage that you're applying to charge a capacitor, which is grounded. Okay. On the output side, and we look into these components. And the output side, you are kind of, it's a voltage, the impact of this that drives this. It's kind of the impact of that input voltage that you applied at the gate. It's like a Vn. Now in NMOS case, it's always inverse the logic. So maybe I should put minus Vn. Just assume it's like a, without worrying about polarity of it. So it's like a voltage source that is driving this from this side. It's like a Thevenin equivalent voltage source, if you remember Thevenin and what was the other one? Norton. So you have a voltage and it has a series resistance. It's not an ideal voltage. An ideal voltage will not have any resistance, but this one, it's not ideal, will have some resistance, and that is really the resistance of the transistor when it's on. And then you have a capacitor from this side. You have a capacitor that is grounded. This is really the drain capacitance. Now the thing that I really want to understand, if you focus on the output side, what I really want to give you idea here. If you apply a step voltage is at time 0, you suddenly go from abrupt 0 to 1. 1 is VDD. And if you apply that ideal waveform here, and there you have a resistance in series, and then capacitor is grounded, the output will be something like this. Now again, I'm not worrying about the polarity. Let's say it doesn't change the polarity. The same input goes output, but the output, when you input step, output is just like this one. So what happens is it starts at 0 and it takes a little bit time to go to close to, still it will take pretty long to go to the, this, oops, VDD, supply voltage. That's where a swing is. And I don't want to get into lengthy equations, but if you look at the current through capacitor, which is C dV by dt, right? And then you multiply that with R and equal to Vn and calculate the output voltage that varies with time. This becomes a differential equation of current. And if you solve that to find the V out, you will get something like this. If you solve that differential equation, the output will be something like this. What is V out? So this is V out. So V out is VD, which is this voltage, the input voltage, the highest voltage that input voltage went to, 1 minus E to the power minus T over RC. Is R is the on resistance and C is the C out or C here or the C drain. Now in this equation, when, this is important, At time t0, when you put this t with 0, so E becomes power 0, which is 1. So then your V out becomes 0 at this point. Then at t for very long time, the V out at a very long infinity, V out becomes Vd, like what VDD is, will reach there. And then if time equal to the multiplication of R and C, at that time output will reach 63% of VDD, somewhere here. What are you getting from this one? So what you're getting, this R and C component, if you make it smaller, this will reach to VDD or this point, or it will be earlier. And the more closer you want to bring this one to the input, the smaller RC is needed. So this multiplication of RC, which is called time constant, is super important. We want to reduce it. That will reduce the delay, because think of that. Oh yeah, I had a bigger picture here. I already explained. Because what happens is, if input is this, if output is this, if you increase RC, output will take longer, which means your delay will be longer. So typically we measure delay between the 50% point from here to here, the 50% of the voltage of the swing, to the 50% swing at the output voltage. The difference between these two is called delay. This is how we measure in SPICE, the delay between two signals. 50% of the time, 50% of this time. So we can, through SPICE simulation, measure this one, and then through equations with R and C, we can measure that one. These hand calculation, or so these equations typically tell you what is the dependency of it. So and the SPICE, and they should be pretty close. But you see that the key thing here is R and C, keeping them low is important to reduce the delay. That's the key thing I want you to take from this. Yeah, delay of the inverter depends on this. But here is a typical scenario, is that you have let's say an inverter. Okay, it's connected to another inverter. And these things, I haven't explained you the metal structure, but these are connected on within a chip through some wires, through the metal structure. So you get the diffusion, the drain connection, go to metals, and then go down to the gate of the next inverter. So how we represent a scenario like this, again, I haven't explained wire interconnect, and I will do a few videos on that, which probably will come pretty soon. So this is our driving transistors. So if you think of just one of them, I'm picking NMOS. It's like a driving inverter, receiving inverter. So when you look at what is the equivalent of the driver side, the driver side is the V in, what a voltage is, kind of creating that impact here. Then you have R and C out. So this is the R resistance on, and this is the drain capacitance. Then this entire wire also presents parasitics, right? It has a resistance, it has a capacitance, and the simplest model that we use is something like this. Again, when we go into wire connect, I will look into a few models how accurately we can represent the parasitics here. But think of this is an R wire, C wire. And when you look from this side, the input, again I'm assuming just NMOS here. What you see here from this side is only the gate capacitance. And that's why. So this is how you can, if you can write in something like this, you can create equations for current and voltage, and you can solve the equation. You can really get the voltage here when you know the voltage here, and the delays through them. So right now I'm not looking into those, but I just want to give you now the next thing is, okay, the inside. So this whole thing is the wire. I'm right now not looking into that. Purely if there is no wire connected, what kind of capacitance you see and what kind of on resistance you see. What is the source of those? So let's quickly get into, first of all, resistance. the on resistance I should say, it has two components. The major component is the channel resistance. Okay, so if this is the current flowing through this one, okay, this electrons flowing to this side or current flowing this side will face some resistance. Now how to get the idea of that? And again I will use some equations, and the beauty of the equation is they kind of give you the dependency of it. You can see the resistance will change with respect to which variable in which way, and that's really the beauty of that. So again, resistance we typically know our Ohm law, V is equal to IR, R is V over I. V is really the voltage, the maximum swing it can have is VDD, right? Our on transistor is with VDD, and I is, this is the current equation. Remember I told you, I didn't mention how I came up with this one, but this is, you need to remember, current is proportional to a constant, technology dependent, then width of the transistor over length, and then VGS minus VT. This is the linear region, and the detail for circuits I told you that transistor operates in linear region, so I have already put a equation there. Now this equation, and it is always good to remember this simple thing, tell you that the resistance, the on resistance of the current of the electrons flowing in NMOS, it's inversely proportional to the width. If you increase width of the transistor, if this factor, everything else remains constant, if you increase W, it goes up. That means the denominator goes up, means resistance will get down. This factor, bottom factor, goes higher, this value of R will come down. So that is inversely proportional. So if you want to keep the resistance very low, what you need to do, you need to have a transistor with very large width. What was the width? Do you remember the width? Width was like, this is the from here, this is the length, and the width is this. Yes, this how wide, how go back. So the more is it, that means the less resistance is it, which makes sense on your current. The higher the area, lower the resistance. Then if you increase the length of the channel, the resistance will increase. So see, that's why we want to keep channels lower, so we have less resistance, and that length is this. So it's in our benefit if we reduce this length, so then current will flow quickly, and that makes sense, right? Then another very important one is this. Remember this VGS minus VT, which is required to turn the transistor on, right? So think that VT for a particular technology, this is constant, and actually you can think of this thing as typically constant unless you try to play with the material, a few other things. So and VGS is the gate voltage, which is equal to the supply voltage, because a 0 and 1 happens between 0 and VDD, supply voltage. So imagine if supply voltage is very high, like 2 volt, 3 volt, 5 volt, like the 5 volt, right? VT is 0.64 for that technology thing, 250 nanometer Intel I mentioned. What happens? The larger this value compared to this one, the higher this bottom factor. The higher bottom factor, the lower the resistance. And you can see that when VDD is very high, resistance is pretty low. But if what we do is, as we as we scale the technology, we bring the voltages down because of power, right? And we will look into the power too. After delay performance, next thing is power. As we bring this down on every technology, this one, it doesn't change that much. So what's happened is we reduce this overall factor, and when we reduce this, resistance increases because it's inversely proportional, and that is what this shows. And that's an important thing you need to be aware of. As voltages come down, resistance goes up. Hopefully that was clear. Okay, then another important component, probably not as this, but still plays into the picture. And if you remember this picture I showed, if you look at this one, this is okay, this is n plus NMOS, right? So eventually you need to connect through diffusion, and you need to go with other thing. So this black, if you remember, this is Intel 250 nanometer research paper picture. What is this? Si3N, sorry, TISI2. I forgot what it's, tungsten silicide, something like that. Okay, they put this one because this resistance that I'm showing, there is a resistance of when you make a contact with diffusion. This is a diffusion layer. And typically when the wire on this technology to 50 nanometer was aluminum, I think. So aluminum directly goes there. There is a on the when you have aluminum coming here and directly goes into N plus material, this barrier is very resistant. So what they do is they include this one so that eventually this is more kind of gradual path there, and current doesn't feel abrupt resistance. So material like these are used to reduce this, but overall point is there's a resistance here when this connection happens, and from the drain side and from the source side, the source and drain, and then there's a channel resistance, this one. So these are the two components of the resistance when you think of a transistor, where the resistance coming from. Okay, what is the capacitance? All right, I think I'm gonna cover it in this video, everything. So capacitance, so think of this one is grounded, this one is the output. So point of interest for us is really the drain capacitance here. So current is flowing here, okay, full of current. Now I'm showing in 3D, there's a current here. So this whole box that you see is drain. You see that I put a little bit here, something like this. I didn't do a job. It's very hard to align this area over this one. So I put intentionally a little bit exaggerated, but it can go here or it can go there. There is an area of drain and source which is kind of gets this overlap to gate and dielectric. Okay, so what happens now? We apply voltage here. There is this dielectric act as a capacitor between two, and this is the connection to, and there is a conduction happening. So you have conduction here, you have insulator, so this acts as a capacitor. So this is the first, is this a good one? Yeah, let's use. So this is the one component of drain to gate capacitance. Another capacitance here is that this region is dielectric, so it acts as a dielectric insulator, and you have here conduction is happening, and here also is connected to ground, so there is a potential here. It's not a conductor, it's a semiconductor, these two. So there is a capacitance, oops, not that one. So there is a, come on, so there is a capacitance here. This thing is grounded. Okay. Now it's important that you look at, in 2D this is good, but in 3D, this whole thing, it has a covered. This area has a depletion. Think of that like you have a PMOS here, and then you have NMOS here. So it's not like it's open on this side, right? Like this is for better visibility, just show you I'm saying. But basically, what I mean to say is, this whole thing on this side is covered with this, right? So this whole thing area that I'm drawing here is a dielectric, and behind that is N plus. So there is really here and on the back side as well, right? There is a there is a P goes around. So there is this side, there is that side, and there is also on this side. There is inside, so there is. So you seeing that? Okay. So it has a and there is a bottom side. Wow, I forgot that. You see at the bottom that we can't see right now, underneath this yellow all the way at the bottom. So there is a component of capacitance there too. Now similar components here exist on the source side. There is some capacitance on source side, but this is all grounded. I'm assuming okay in the linear region is this is where is the major contributing factor, because this is on a higher voltage. Right? So you understand the capacitance sources of capacitance there. So if somebody asks you, okay, what are those components when intrinsic components that within the transistor that creates that capacitive load or kind of a parasitic capacitance? So these are those ones. So this one you can also assume when you write it in this capacitance, you can assume that okay, this part is in term of eventually what you write it in mathematical, you just have all these capacitors kind of one side grounded. You just add up the values of all of them. So you have C drain to gate. It's a kind of a Miller capacitor. If you look at this, there's a swing here, there's a swing here. And when two conductors are swinging in different direction, the net effective capacitor can be much bigger. So this is a critical capacitor there. But you can write it into ground form too. If you remember the Miller capacitor, you can cite that and understand that. So I will write everything in. Okay. So then this, let's call this C drain to bulk, and let's call it side. Drain to bulk side S1, and this is like same thing, plus C drain to bulk side 2. What should, let's call this thing as side 3. Side drain to bulk side 3. Oh, there's this guy too. You call drain to bulk bottom. So add these 5 components. That will be your equivalent of this. Add up all them, that will be your C out. And the resistance of the 2 components I told you. So, and the voltage that is coming here. And then you can solve everything. Right? So those are the component and resistance capacitance and how they affect the delay. And I told you delay definition is really from 50% of the input to 50% of the output. Yeah, and this is how later on it will come in a static timing analysis as well. So I thought it's good to give you in that overview. So keep resistance and capacitance down, and that will be good for delay. Okay, hope you understood that. Let me know. Thank you so much.